Hello. So we're going to do a couple of problems on the chapter on Jordan forms. So the first one is I give you a 3 by 3 matrix C, and the problem is we're going to put this into Jordan form, find out what the Jordan form of this matrix looks like, and also we're going to find the P matrix that changes the basis to put this matrix into Jordan form. Now, it doesn't tell you in the question, but I'm going to make life a bit easier by pointing out that this matrix only has one eigenvalue. And if it's only got one eigenvalue, then from the trace you can see that eigenvalue has to be lambda equals 2. And it's going to have algebraic multiplicity 3. So to get the Jordan form of this, what we need now to do is to look at the kernel to try and find the eigenvectors. So we're going to look at the eigenspace for 2. And that's the kernel of the matrix we get by subtracting 2 off the main diagonal. So we subtract 2 off the main diagonal, and we stare at this matrix for a minute, and we see that it is in fact rank 1. So when you're doing these things, you've got to be careful that you get the right dimensions worth of eigenvectors. So I look at this, and this is a rank 1 matrix, because multiply that by -1 gives you that, and by -2 gives you that. So it's therefore got nullity 2, so there are 2 eigenvectors hiding in this kernel. 2 linearly independent eigenvectors there. So keep it simple. If I look at the first and the third columns, I'll have one of them, I'll get rid of that and take one of them. And that will work. And to get the second linearly independent one, I'll have to use the middle rows. So what will I do? I might get rid of the first one, I'll take one of those and 3 of those. The representations are not unique for these things. So that tells me then that this matrix has, that lambda equals 2 has geometric multiplicity 2. So I'm going to draw up my onion immediately. I'm going to draw up the onion diagram for this one. So in the innermost kernel, I've got 2 eigenvectors. So innermost kernel 2, I put 2 crosses for the 2 eigenvectors. Now it's a 3 by 3 matrix, so it's going to have 3 generalized eigenvectors. So to get the next generalized eigenvector, I'll have to go out to the next kernel out to pick up my 1 extra generalized eigenvector. Now, I will get the P matrix in a moment, but just from that information we can write down what the Jordan form looks like. So this matrix then is going to have, there's going to be 2 chains. There'll be 1 chain you can build in there, and there's a trivial chain which is just that single eigenvector there. So that tells me, the fact that there are 2 chains tells me there are going to be 2 Jordan blocks for this matrix for lambda equals 2. So there are 2 Jordan blocks. And the length of the chains tells me the size of the Jordan block. So I'm going to have 1 Jordan block of size 2 and 1 of size 1. So the Jordan form for this, I've got a block of 2 by 2 block there, which is going to then look like this. So it's 2, 2, 1, 0. So there's the 2 block. I'll just put a little sub-matrix around this just to emphasize this. So there's the 2 Jordan, the 2 block. And that will correspond to this 2 chain here. And then I've got a simple block of size 1, so that's just a single 2 there. You can think of this as a 1 by 1 Jordan matrix, and then you've got zeros everywhere else. And we can write this using our notation. I can say this is a block of size 2 based on the eigenvalue 2, and I've got 1 block of size 1 based on the eigenvalue 2. And if that's all I'm interested in, if I just want to know the Jordan form, that's all I have to do. However, the question asked us to go further and find the P matrix that puts this matrix into its Jordan form. And to do that, I need to get the generalized eigenvector. I've got to find an eigenvector in that outermost kernel. And I get that by looking at the kernel of C minus 2i all squared. So I now go out to the next kernel, and I can see there that I'm going to get 3 generalized eigenvectors at this stage. So this kernel is going to have 3 linearly independent vectors spanning it, so that means it's got nullity 3 and rank as 0, and if it's rank 0, then this is just the 0 matrix. So this is just the kernel of the 0 matrix. So, now people do various things here. Some people say, oh, well, because it's the zero matrix, I can just write down the standard basis vectors for this, and that's fine. I like to just remind myself what's happening. I've already got two of them, so I'm going to keep those. So they're the two eigenvectors in here. And all I need now is another vector, keep it simple, that's linearly independent with these two. So, by the way, you know, I could put 10 minus 16, 35, that will work, but it's not very useful. So keep it simple. I'm just going to take something like 0, 0, 1. It's pretty obvious that if you use that 1, you can make that 0, 0, and you've got your standard basis vector. So it's obviously linearly independent with these two. And it's going to be in the kernel of this vector, of this matrix. So now I take this vector here is the one I want. This vector here is going to be this vector here, 0, 0, 1. And now I've got to build my chain. So I need a chain of length 2. So I now build the chain. So don't forget the chain's the important part of it. So I get 0, 0, 1, and I multiply by c minus 2i. I multiply by c minus 2i. That's, be careful with that one. So c minus 2i is going to be this matrix here, because that's where I got that from. So multiplying by that is simply going to pull off the last column of this matrix. So I build that chain. Now, by the way, this vector now has to be, this vector has to be in the span of these two. I've now changed my way back in, so I'm somewhere in this kernel, and that's got to be a linear combination of those two. And it's pretty obvious if you take that one minus that one, it does the trick. Just a little double check to make sure everything makes sense. So there's the chain. So finally, I now put this into my P matrix very carefully. Now I chose to put, it doesn't matter whether you put the 1 block up there and the 2 by 2 block there. I like to order it by sizes of blocks going downwards. So I put the 2 block there, that's going to correspond to the chain. Now be careful the order in which the chain goes. So the chain goes 1 minus 1 minus 2 and then 0, 0, 1 in that order. So that's the chain. And that 2 chain is going to build this little Jordan block in here. And finally, for my third vector, I just need to toss in any eigenvector, because that's going to build this block here, any eigenvector I like that's linearly independent with both of these two. So you can pick either of these. I'll just pick the first one will do. So 1, 0, 1. So this one here is any eigenvector that's not in the span of these two, and clearly that's not. So there's that's my P matrix, not J, I've got J, there is my P matrix, and then the theory guarantees that if I do P inverse CP, then I will get this J, which is this Jordan form.